All right. Atoms, atomic number, protons, electrons, neutrons. Okay, so if you're watching the video, look in quizzes, look for ions, atomic number, protons, electrons, neutrons. Identify the description of an atom. Which one of these is it? Let's call it A, B, C, D, and E.
C.
C is protons and neutrons and the nucleus and electrons and orbitals. That's right. So the other day when I described it, in the nucleus is protons and neutrons, and electrons are in orbitals. It's kind of a simple question. There was more that we did the other day. Do you remember what the atomic number is equal to?
Number of protons.
Yes. So if you look at your periodic table, the integers that start with 1 at the top left, they go to 2 at the top right, they go to 3 back over on the left. Those are the atomic numbers. And that's the number of protons. So again, this database of questions you're looking at, a subset of these will be on the test. For the same element, ions differ how?
Electrons.
Yes. Predict the charge on an aluminum ion. 3 plus. All right, let's get down a little. Determine the number of electrons and protons in gallium plus. You have to find gallium on the periodic table. It's in column 13, third one down. So how many protons does it have?
31.
Necessarily, it has 31. But if it's gallium plus, how many electrons does it have? 30. If it's plus, if it's 1 plus, which it is, given what it shows here, it's lost 1 electron, so it's 30. Question 8, atomic mass of cadmium. This is just seeing if you can read the periodic table correctly for what's there. The atomic mass of cadmium, is, it's in the 12th column. Yes, so the numbers there, the atomic mass is 112.41. The 48 is the atomic mass, the 112.41 atomic number. 48 is the atomic number. And 112.41 is the atomic mass. The 1.7 in the bottom right won't come up for a while, but that's the electronegativity. You guys know this, charges on protons, neutrons, and electrons. If this was A, B, C, D, E, what's the answer? B, it's this one. Atomic number. What element has atomic number 7? You just look for that integer. It's a little tricky because it's down at the very, very bottom. You guys see it? It's one of the weirder names. But this is just a matter of you using the periodic table, and you're going to have that on the test. So be able to use it. How many protons does bromine contain? So bromine's on the right, column 17, 3 down. You see the 35 there, that's how many protons it has. Okay. How many electrons, this is number 19, how many electrons does calcium 2 plus possess? So if you look at calcium, it's column 2, 3 down. Calcium. If it's neutral, it has 20 protons and 20 electrons. But if it's +2, that means it's lost 2 negative charges. Those are electrons. So if it's going to be 20 minus 2, which is 18. Everybody good on this? This is pretty straightforward. Let me put on camera something real quick. These two things, I still don't have quizzes up for. So this quiz I'm going through right now, that's two things we went over that it's not in these quizzes yet. I'll get those up soon. Not going to see you guys until Wednesday of next week, so I'll have some time to get this done. But I am going to cover some other things. What else should we cover? How many electrons? How many electrons? Question 23. How many electrons does copper have? That's Cu, copper, that is column 11. If it's 2 plus, that means it's lost 2 electrons.
27.
Yes. So you see 29 there for copper, Cu. It's lost 2 electrons, so it's 27. We're good. All right, so that's there for you guys to go through. There's more there, but it's just that same fundamental stuff we were doing. Oh yeah, you know what else? One more thing. What is it that I still don't have? I'll think of it, but you're still missing one thing that I covered last time. But what I'm going to do is start isotopes. Isotopes are something we'll cover kind of as a tangent, and then we're going to come back to the main topics, and we'll kind of leave isotopes behind. Isotopes are related to neutrons. Neutrons. I misspell this a lot because of nucleus. Relative mass. The first thing to know that protons are very heavy, neutrons are very heavy, electrons, negligible. When it comes to how much an atom weighs, it has everything to do with the protons and neutrons in the nucleus. And the electron is so light, it practically doesn't contribute to the weight. Electrons are about 1,000 times less heavy than protons and neutrons. That's the first thing to know. I'm going to bring up this thing on isotopes. I have a couple more quizzes ready. So E is element symbol. It's Cl for chloride, S for sulfur, etc. So just kind of as a variable, I'm going to put that there. I'm going to say, we write the mass number up here on the top superscript, and down here we put the number of protons. And that is the atomic number. So you're familiar with that. Mass number, put it over here, is so this is just a convention, the way atomic symbols are written sometimes. And you put the charge up here sometimes too. But y'all are familiar with that. That's put 2 plus for magnesium or negative, 1 negative for chlorine. But this is really kind of what I'm getting at right now, mass number. So if I wrote down, let me find one here just so I have a real example. You see question 3 in the quiz on isotopes. It says this, AG109. And 47. So there's 2 different ways we represent isotopes. Isotopes are where you have protons equals, and I'll just do this as neutral atoms, equals, but you can have charged isotopes. And let's say you have I'll do Ag. This is silver. If you have 47 protons and 47 electrons, the other day you would have told me that's a neutral atom, right? But I kind of didn't talk about neutrons at all last time because I wanted to save isotopes for one specific day so we could cover it and then get past it. Right. Stay with neutral atoms just to keep it simple. I would have to look it up, but I'm just going to kind of make it up. Let's say it has what I'm showing here under AgU silver is protons are 47. That defines silver, and that's what's written here. That's the atomic number. And I said we'll just stick to neutral atoms for this discussion. So both of these 2 different atoms have 47 electrons. It is possible for atoms to have different numbers of neutrons. So picture a silver atom that has 47 protons and 48 neutrons. And this one has 47 protons and 46 neutrons. Those are isotopes. That's what isotopes are. They differ in the number of neutrons. Basic definition of isotope. All right. So if you see a symbol like that, and I say, many neutrons does this particular isotope of silver have? Based on this definition. This is atomic number, which equals the number of protons, number of. And the mass number, written up here, is protons plus neutrons. So how many neutrons does this particular isotope of silver have?
62.
All you have to do,
Yeah. 109 subtract 47.
yes, exactly.
62.
That comes to 62. 9 minus 7 is 2. 10 minus 4 is 6. 62. Can y'all see that? This seems very erudite. Maybe it's confusing, but it's actually very simple. 109 it's called the mass number, and that's the neutrons plus the protons. And 47 is the number of protons. So all you have to do is subtract the number of protons from the neutrons. Let me write it like this. I forgot something. There's something I went over the other day. I can't remember what it was. Let me write it like this. How many neutrons? This was, okay, what was it? 147 and 109? It's literally this. 109 minus 47. You guys okay with that? That's one way we represent isotopes. And again, we'll talk about isotopes for a little bit, and then we're just going to ignore it for the rest of the semester. Eraser. The other way we represent isotopes is, I guess I'll write it right here. You might see so this and this, that's just two different ways to represent the same thing. The ACS test tests you on both of these two slightly different nomenclatures. But notice this and this are literally synonyms. If you look on the periodic table, 47 is with AG, AG is with 47, they're inseparable. And I did say the other day that the number of protons defines the atom. So if it has 47 protons, it's silver, it's AG. So this is kind of a given. This and this, having this, AG, and 47, this together, is absolutely redundant. But it's a convention. You still see symbols written like this. But if you look at the periodic table, 47 protons means AG. You see what I'm saying? So don't let that go over your head. These are just kind of obviously connected. This is what tells you how many protons there are. This is protons plus neutrons. You guys are with me? So if you got a question like this, AG 109, how many neutrons? How many neutrons? You just have one more step to do than you had if you got it this way. Now you have to look up AG on the periodic table and find the 47 so you know what to subtract from 109. So if it's in that form, AG-109, you just have one more step. You look up AG on the periodic table, you find 47, then you can subtract 47 from 109. That'll tell you how many neutrons. You guys with me? If I forgot anything, we'll see it here. AG-109. This is still something I did with ChatGPT, but these are still good questions. This one's just weird. You see protons? You're really looking for the one of these. No, this one, that's a bad question. That's one I didn't fix. Okay, how about this? See if y'all can answer this. Nickel 59, how many neutrons? So it's like this.
24, 32.
If we're given that, you're asked how many neutrons? I trust that you had it, even though I didn't hear you, but look up nickel on the periodic table. It is,
34, it's 28.
Isn't it its
which column? Yeah, okay. Column 10, look at column 10. So what's the atomic number, AKA the number of protons? You all see that? 28 protons. 9 minus 8 is 1, 5 minus 2 is 3. That's the number of neutrons.
So for the mass number, would you just round up or down?
These are always going to be integers. These are always going to be integers. I probably should have said that, but if you have one proton, you have exactly one proton. If you have 2 protons, you have exactly 2 protons. These are exact numbers, if that helps, but they're integers.
Yeah, just on the periodic table, it's like 58.69. So
Oh, no, you're looking at the wrong number. I'm glad you asked. Nickel, you're looking at 58.69. What you should be looking at is the 28.
Yes, but for the mass number.
That is, well, okay. That is a good question. The mass number. These two things are different things.
Yes, I understand.
The mass number is not on the periodic table. The atomic mass is on the periodic table. You guys see that?
Do you want us to, for the atomic mass number, do you want us to round up or round down? Like, do you want us to round, or do you want us to use the 58.69?
So if we were talking about nickel, 58.69?
Yes, sir.
Don't round it. Anytime you use it, that's 4 digits of significance.
Okay, so always use the whole atomic mass.
Yeah.
All right.
But I haven't done anything with atomic mass yet.
And the atomic mass is the average, and the mass number is the specific atom.
Yeah, I'm gonna save,
Or the
kind of
specific
how you
isotope.
derive this from natural abundance and all.
Okay.
Until next time.
All right.
But that does come from isotopes.
Yes.
You're remembering that from another chemistry class, right?
But when they ask us to find the mass of a specific, like of a specific atom, you find the mass number.
Yeah, if you're gonna find the mass of that specific isotope, you
Yeah,
do
yeah,
need the mass number.
Okay, thank you.
Okay, but I'm not gonna quite go there yet. Two different ways.
That's the average mass.
represent that. Question 6 in isotopes. Isotopes differ in the number of, this should be obvious. A, B, C, D, or E,
All D.
different number of neutrons. That's what isotope means, different number of neutrons. It means you're talking about the same atom, you might be talking about potassium and potassium, but they'll have different numbers of neutrons. So, this is number 8 under isotopes. C227. Okay, how many neutrons is that?
It's 138.
This one you don't even have to look up because it's got the protons here, the atomic number, and the mass number, which is protons plus neutrons. So you just do this. It's 138. This question asks how many protons also, but the protons are right there, right? Okay, good. Okay, there's good questions there. Let me open this. So y'all can see it. I'll do a little more on isotopes with that relative abundance stuff. But I've had a hard time finding good questions on these. Between our textbook and my previous textbook, it's not great. How many of you took chemistry before? All right. You love moles, right? You understand moles? She gave a thumbs up. Most people go, no, I hate that. I'm going to do that next. But get some water there. I figure it's because this class is at 8 a.m. But my 2 p.m. class, almost perfect attendance. Since Monday, we had like half attendance. I hope whoever's not coming is getting a lot out of these videos. It's a stark contrast. I'm not a morning person. I would probably miss some morning classes. So do you guys. Moles. Okay. When it comes to moles, there's this number. We call it Avogadro's number. Those of you who have taken chemistry before, you probably recognize that number. That's Avogadro's number. I'm not going to talk about that yet, but realize that's an integer. That means 6.022 And really, we know more digits out this way, but we'll just stop there at 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 16, 17, 18, 19, 20, 21, 22, 23. That's really what that number represents. It's an integer. I mean, we always consider it an integer to some significant figures. But that's how far, oh, I should have put this here. No, I shouldn't. All right. 4 significant figures. But let me not talk about that. We can talk about something you know about, dozen. You've heard of dozen. Means 12, right? Dozen is what I call a counting number. Here's another counting number. One score equals 20. Just in case you don't think you've ever heard of that, you've heard of 4 score and 20 years ago? You ever heard that?
100 years ago.
4 score and 100 years ago. Gettysburg Address. The first time I heard this described, oh, this is where, you know, everybody used to talk. They do numbers that way. During the Civil War, people still said that. Like if you meant 85, you'd say 4 score and 5. But then by the time the Civil War came along, where America fought the British, that was gone. Everybody would have said 85. That was a new way of speaking back then. And he said 4 score, and what is it, 4 score and 8 years ago? What did I just say? 4 score and 87 years ago? The Gettysburg Address was like the addressing the nation at the end of the Civil War, we all come back together. And he was trying to be nostalgic when he said 4 score and 7 years ago. And here's the cool thing, 87 years prior was the revolution against the British. He was hearkening back to when we were unified and fought the British, and he was being nostalgic by using that type of language. Anyway, I like that little bit of trivia to say. And here's one more counting unit. My way of wasting a little class time, talking about history. I'll do pair. These are counting numbers. And if I do some math with these, I think you'll understand every bit of it. But what I want you to realize is one mole spelled out is, but that's how we abbreviate it, is that integer. I could literally put that right here. It's the same thing. It's a counting number. Speaking of dozen, if I told you to walk outside and count the cars in the parking lot, and you counted 18, you'd walk inside and say 18. 18 is the number of cars in the parking lot. But if I said go out there and count how many dozen cars are out there, you'd actually come back and say 145. And what I'm distinguishing here is a dozen. I want to remember this. Quizzes I still need to put up. There's one other one. I got to remember that. One dozen equals 12. Now, DOZ is dozen. All right. I said earlier in the semester that every numeric value we work with is has 3 components. the numerical value, and then there's units and a label. The numerical value might include a power of 10, but for now I won't bring up any powers of 10. So let's say it was cars. I sent you out in the parking lot. You counted 18 cars. And what I want to point out is, if I told you to go out there and count cars, and I didn't say some counting unit, like score or pairs, you'd come back and you'd say 20 cars. If I ask you to count dozens of cars, you come back and say 1.5 dozen. And similarly, if you did score or pair, it would be some other number other than 18, right? What I'm trying to point out is, when you're using those natural numbers, the integers, the counting numbers, when you were in 5th grade, if they said count something, you go count them. And there would be nothing here for counting units, because you weren't using any counting units. Counting units, mole, pairs, dozen, score, are different from all the other units we typically work with, like grams and volumes and stuff. Counting units are a little different, but they do fit in their own category. But the point is, if you're not using any of these counting units, one mole equals that. One mole literally fits in this list just the same way as everything else. If you're not using the counting units, my point is, you see here where I say there's a numerical value, units, and label, there won't be any units. There'll just be a space there. If I send you out in the parking lot, and I don't say count dozens, and I don't say count score, or pairs, or moles, of course, if it's a parking lot of cars, because look how big that number is, I wouldn't use that number. But if I didn't say that, you come back and say 18 cars. You would say 18 cars. If I said go count dozens, how many dozen cars are there? You come back and go 1.5. I put the label in parentheses just to emphasize that it's nothing numerical and it's not units. It tells you what this number refers to and in what units. Okay, so that's a kind of a cue when you're solving problems like this. But let's say you went out there and you counted 18, and again, notice there's a space here. And I still like to put things over one. And you came back and you said it's 18 cars. And I said, well, what is that in dozen? You would use this, actually this, because you would write it this way instead of this way. And you want cars to cancel. Space. That will tell you how many dozen cars were in the parking lot. Even if you counted it, I'll leave this up here. One mole equals 6.022 times 10 to 23. I hope I have the right number of zeros there, but these are equivalent to each other. What else did I have over here? You always have a numerical value. And the label tells you what that numerical value is referring to. And the only time there's not units is in those natural counting numbers. the 18 that you went out and counted. That you went out and counted cars. So if you go out there and count 18 cars, and you walk in and you go, it's 18 cars. And I go, oh, wait a minute. I wanted that in dozens. You know the relationship between dozen and just counting numbers is 1 to 12. You could set up this relationship and calculate what that is in dozens. The labels always go with the unit, even if there's no unit. Those go together, asterisks. Those go with each other. Meaning, blank cars cancels blank cars. The units left, and like I said, units, counting units in this case, go with the label. So if we cancel that, we have dozen cars. And the rest is just doing this, which is ultimately 18 divided by 12. And my calculator says 1.5. 1.5 dozen cars. Realize, let me do this next. If I told you to go out there and count the stars, or like sands on the beach, you'd come back with a number like, like a scoop of sand or stars in a certain radius that you look at. Unless you say you had something huge like again, no unit, because I just asked you to go out there and count 1 cup of grains of sand, or 1 sphere in the sky of stars, some huge number. And you came up with this huge number. Notice this is 10 to the 19, so the decimal goes 19 places. It's a huge number. But if you actually did manage to count all those, and I didn't say dozen, and I didn't say score, and I didn't say pair, and I didn't say mole. You went out there and you counted all of them. If you did that, there's no unit, no counting unit. There's a blank here, and let's say it's stars. You would go, that's what I found when I went to count. And then I could say, now I'll use this because all those zeros are cumbersome. But I want you to see the similarity to this. I think I can erase that. I'll write it up here. I wish that cross wasn't there, but let's say you got space, labeled, stars, I'm going to put it over 1, and then you're going to use this relationship. All right, this side has 1 mole. That's a 1, and the mole, and this is general, so there's not a label. It's kind of whatever you want, whatever you're counting, you would put here as a label. So you've got the numerical value and a unit, aka a counting unit. And on this side, you have a numerical value and no unit. And again, still no label because it hasn't been applied yet. But if we're going to say it's stars, we've got number, space, as in no unit, and stars. So like I told you before, I'm I'm gonna say 1 mole, and I'll go ahead and make it in terms of stars. Is 6.022 times 10 to the 23 blank, where the unit would be. This is this relationship just written as a ratio. Do you see that? So if you ever see 1 mole equals 6.022 times 10 to the 23rd, you could write it this way with an equal sign, or you could write it this way as the ratio. This is how we're going to use it. And either we're going to use it like this, or we're going to use it flipped over. And space. Doesn't look like a rectangle. We're going to use it one of those two ways. As usual, when you have something like that, you're either going to use it this way or you're going to use it flipped over, depending on the situation you're in. Situation we're in is here. I just did that to make a little space. So now, and what I want you to realize, I want you to see the similarity. If I wanted to know how many dozen, you went out and you counted 18, and then you came in here and I said, oh, wait a minute, what is that in dozen? You use your relationship of 1 dozen cars to 12 blank cars. The blank cars cancels with blank cars, and you could find out that it was 1.5 dozen.
Okay, so, but if you were to apply the units and label, it would be like, I don't know, like 12 grams of carbon, like carbon would be the label and grams would be the unit?
Yes.
Okay, all right.
So where am I? So it's number blank cars. This one is number, a huge number, blank stars. So now if you wanted to calculate how many moles of stars this is, you would go, we're going to use this because we need blank stars to cancel and we need moles to survive. So we need this on the bottom, so we're going to use this, not this. That's kind of the whole point of me pointing out that there's a space there. This helps you solve these types of problems. If there's not a unit, it's just those integers. This is an integer. Don't let it fool you. That's just some huge, huge number.
Is there a way to do this without having to do like the cross multiplication and all the fractions and stuff like that? Like a way to make it simpler?
I do this the most formal way and the most obvious way. There's algebraically equivalent ways to do this. Ends up being the same thing. I could set up the way I do it, and you could go, well, the way I think about it is this, and I could rearrange it using algebraic rules and show it the way you're thinking.
Could you try that one time?
Well, you have to tell me the way you're picturing it.
Okay.
But let me finish this thought. All right. Okay, y'all, so I'm going to use this, 1 mole. So if you went outside and counted how many stars, and you counted this huge number, and you wanted to know how much it is in moles, that's how you would solve it. And what I want you to see is the similarity to this. Because so many students have trouble with moles. If you understand dozen, then you do understand moles. What's boggling your mind is how huge this number is. But that is an integer, just like 12. You guys with me? Having said that, that's what it is. What I've just explained. Those are the three things I still need to make quizzes. Let me take this a step further, and this is the actual quiz I have up there for you to practice. If you define things in moles to begin with, then that 6.022 times 10 to the 23rd never shows up in any calculations. Let me tell you what I mean. Look at your periodic table, and let's take nitrogen as an example. You see that number for nitrogen? That's the molar mass. The atomic mass for nitrogen is 7. The mass number varies depending on how many neutrons are there. So the mass number is not there. But that 1401, that's the atomic mass, the formula mass, if we're talking about formulas. But 1401, let's just call it the atomic mass right now. 14.01. The units here, if we sort of leap out of thinking about neutrons and isotopes, that's the units on that 14.01. They don't typically put the units on the periodic table. It's equivalently AMU, atomic mass unit. I'll come back to the atomic mass unit as related to isotopes. That's when you use the relative abundance. But don't think about this right now. I want you to think this way. 14.01 grams per mole. That's what this means. It does also mean this. So I like to point out that the numerical value is equivalent. There's a conversion factor that gets you to one to the other, but I'll skip that. But grams per mole, meaning if you have again, that's an integer. If you have that many things, whether it's grains of sand or stars or nitrogen atoms, that's 1 mole. But this is already defined in terms of moles. If you have that many nitrogen atoms, that is 1 mole. And if you put this many atoms of nitrogen on a scale, it will say 14.01, a scale that measures grams. You guys follow that conceptually? That's the whole point of this number on the periodic table. So let me put it this way. I have 3.61 grams of nitrogen how many moles is that? And this number won't show up in this calculation. Really, the key to realizing that the 6.02 times 10 to the 23rd doesn't even show up in the calculation is when there's not a blank where the units go. This says, I have 3.611 grams of nitrogen. That thing I said before, you've got 3.61 numerical value, grams, unit, nitrogen. Like, if that's missing, if there's not a unit, then you use the 6.022 times 10 to the 23rd. That's why I was emphasizing that. I would go like this and say, see, there's no unit. If there's no unit, if there's not grams, if there's not, meters, if there's not some counting unit, it just said 3.61, that would mean there's 3.61. Actually, fractionally, it wouldn't make sense, but you see what I'm saying, the missing unit? This says, I have 3.61 grams of nitrogen. How many moles? That's a unit. It's a counting unit. So if you have a unit here and you're being asked for something in a unit, 6.022 times 10 to the 23rd won't show up in the problem at all. That's worth knowing. So the way you would solve this, nitrogen, I will put it over 1. All right. I've told you all already, the thing you want to do when you see units written like this, the 14.01 goes with the grams, and a 1, an exact 1, goes with the moles. So go ahead and write it. Grams. And of course, you might use it flipped over depending on the situation. It might be this. And I haven't attached a label here because this is true in general. It doesn't matter what the label is. But in our case, the label is nitrogen atoms. So we've got grams on top. We're being asked for moles. So we need moles of nitrogen atoms here and grams of nitrogen atoms there. That'll give us moles of nitrogen. You see that as an outline? I haven't filled in the numbers here yet, but I needed grams to cancel. I need to get the moles. That's moles per grams or grams per mole, however you're going to use it. We're going to use where moles is on the top. That'll tell you how many grams, how many moles this many grams weighs. You see? So these types of problems are more simple than using 6.022 times 10 to the 23rd. And this is really the goal of chemists, to get away from those huge numbers and we just work in moles. And believe it or not, 6.022 times 10 to the 23rd doesn't show up, and most of the time we're working with this.
So you're saying instead of using that number, you want us to do like 6.0, or you want us to use this conversion method?
Yeah, my point is, if you get I'll show you a question that doesn't have a unit, and maybe it'll be more obvious.
Okay.
When it doesn't have a unit, when there's a missing unit, that means the 6.022 times 10 to the 23rd shows up. In this case, you're given something with a unit, and you're asked for something with a unit. There's nothing missing its units, so 6.022 times 10 to the 23rd won't show up.
Okay, but when there's no units, that's when we use it.
Yeah, when there's no units. I'll do one like that next.
Okay.
But I just know this is where students get confused. They'll look at a problem like this and they'll go, where's 6.022 times 10 to the 23rd? That's the big deal about a mole, right? 1 mole equals 6.022 times 10 to the 23rd. And it's like, you're like, when does that show up? How did that not show up in this problem? That's what I'm trying to emphasize. It's when a unit is missing. When it just says a number, and doesn't give a unit, like it would say some number of nitrogen atoms. It won't be some number of grams of nitrogen atoms. It won't be some number of moles of nitrogen atoms. It won't be some number of some other unit of nitrogen atoms. It'll be this many nitrogen atoms, just like 18 cars in the parking lot. It's that natural number of counting numbers that you used when you were 5 years old. But we just happen to be dealing with huge numbers. Even a tiny scoop of any group of atoms is a bajillion freaking atoms. So we deal with these huge numbers when it comes to atoms, just because they're so tiny and we're so big in relation to them. If we're going to work in a lab, a little tiny bit in the palm of your hand is about a mole. 6.022 times 10 to the 23rd freaking atoms, a tiny little bit in your hand. So we don't use dozen, we don't use score, we use mole because it's a huge number, and that saves us a lot of crap. As long as we've got a relation for every atom on the periodic table, grams per mole, then we can stick to this much more simple way of looking. If I solve this, it's just 3.61 divided by 14.01, 3 significant figures. My calculator says moles of nitrogen atoms. I could say nitrogen atoms, I just put in there, just to indicate it. Of course, 3 significant figures, 4 here, so I'm keeping those, 6 rounds to 7, so 0.2. You guys okay with that? Any questions? All right, the only other way you get a question like this is instead of grams, you'll be given moles and you'll be asked for grams. And this is still dodging. I said I would do it next. I'll do it next.
Earlier when I asked like other ways to do it, couldn't you just do 3.61 divided by 14.01?
Yeah, but notice that's the phrase I said, algebraically equivalent. You see that what you just said is algebraically equivalent to what I've got here. What I put in my calculator is 3.61 divided by 14.01.
Why do you like set it up like that, like adding?
It's just the formal way to go. It shows all the algebra in an explicit way. If the way you think of it is, if I'm trying to get from grams to moles, I divide by 14.01. If I'm trying to go to moles to grams, then I multiply by 14.01. That works.
Okay.
This is just the really formal erudite way to do it, and that's the way I always show students. And if you do it some other way, hopefully you can connect it to this so it like all clicks. But I do this a formal way because it looks the same way every time I do it. All right, so let's do one where I'm going from moles to grams. Some number of moles of nitrogen. How many grams? Let's say we have, I'll still do 3.61, whatever. Now let me change it so it's not confusing. How many moles should it be? 19.6, there we go. If you're asked a question like this, you go, okay, there's moles there, and it's asking me for grams, 6.022 times 10 to the 23rd is not going to show up. Meaning, this very fundamental definition that we shove down your throat when we get to this part in chemistry isn't even going to show up. We're going to use the relationship on the periodic table to solve this, just like we did before. So for this case, I would go moles. I'm going to use this one this time because it's grams per mole. I need moles to cancel. One mole. And in this case, I'm essentially multiplying across. This is what he was just asking. I suppose the simple way to remember it is if you're given moles and you're trying to find grams, you multiply by what's on the periodic table. If you're given grams and you're trying to find moles, then you divide by what's on the periodic table. I'm just showing you the formal algebra. So this time we calculate across 19.6 times 14.1. Calculator says and cancel the mole. I should have done this. I should have the label there. Just to be complete, this is grams as well. So grams of nitrogen is what survives. I haven't done significant figures yet. 3 here, 4 here. Okay, this has to be 3, the 5 rounds to 4. This one with 275 grams nitrogen. I can show you real quick the quiz I made for this. I have the quiz I'm working on that has the numbers of the 6.02 times 10 to the 23rd. Okay, there you go. So question 1, it's called moles working. I could rename it now because I'm not still working on it. But I already opened, so I'll just leave it like that. But moles underscore working are the quizzes. Number 1, 2.63 moles of nickel have how many grams? What do you need to find first? Well, let me put it like this. Where are you going to look first? Periodic table. You're going to look up nickel. I meant to put the names and symbols in here. Nickel is Ni. We already talked about that. 58.69. That's what you need. Uh, 2.63. And it's worthwhile if you're new at solving these types of problems to write it down like this. That's moles of nickel. So numerical value, moles, and I. Numerical value, unit, label. And then you're asked for that many more. What is the mass in grams? So you're being asked for grams. The question mark is, unit label, the question is, what's the numerical value of the gram? So this is your question mark. Meaning, equal sign, there's going to be some numerical value, grams of nickel. You know that just from the stating of the question. You're given this as an input. Unit, label, I'm going to do my 1 again. And what you need here is from the periodic table. What did I say that was? What does it say for nickel?
58.61.
58.69. And just go ahead and stick on the end of that, grams per mole. It's always grams per mole. Everything on the periodic table is grams per mole. Not everything, but the atomic weights are in grams per mole. Also, they could be in AMU. I'll get back to this. 8MU atomic mass unit. But I'll get back to that. I'm going to talk about isotopes again. So 58.69 grams per mole, but I would tell you to go ahead, especially if you're struggling with these types of equations. Go ahead and turn it into that. And also realize you might use it like this. You're going to use it one of those two ways. And when you look here, you see that moles of nickel is on top. You're going to need moles of nickel on the bottom, so it'll cancel, and that tells you which one of those you're going to use. You're going to use moles on the bottom and grams on top. Grams of nickel. And that's going to give you the ability to solve for that. And it is ultimately just multiplying 2.63 times 58.69. 3 significant digits, 4 significant fidgets, 4 significant fidgets, 2.63 times 58.69. My calculator says 154.3547. Did you calculate it too?
Yes.
Is that what you got?
Yes, and then it rounds down to.
Yeah, 3 significant figures. We've got those. The 3 does not round to 4, so 154. Hopefully, yeah, that's your, so that's it. Those. This is for me to remind me that I need to give you guys practice problems. Number atoms. I need to give you some that do involve this, that are missing that unit. But I'm not quite prepared for it yet today. But I'll give you some of these where it's missing a unit, and then it'll help you distinguish between these. The other thing is, oh yeah, you're gonna need problems. Just have a picture of that so I don't forget. That'll give me something to do over Memorial Day. Y'all got fun plans for a long weekend? Good for you. At my age, fun plans is the same thing I always do. I just want to be at home, chill out in my chair, watch cartoons or some old shows or something.
You could do some things.
I'll go visit a family. But most of the time, I'm just going to chill.
Does your family live close by?
They live in North Georgia, where I used to live. They're about 3 hours. I got one more thing I want to do. Before we leave. All right, y'all. Pay attention to one more time.
Just keep the GPS.
Let me show you all a formula now. This is very straightforward too. I don't have any problems up yet for it. But this is just another very fundamental thing to know. Based on what we talked about last time, FETO And let's do NaCl. So ionic compounds. MgO. I'll go with these. Okay. Watch this. It's pretty simple. This is formula mass. So in the same way that we were able to deal with moles with atoms, we can also deal with moles in actual compounds. And it's pretty simple. You do it like this. I always write it this way. I think it's very straightforward. Fe, there's 2 of them. Oxygen, there's 3 of them. Look up Fe on the periodic table. 5585. Oxygen on here, 16.00. So what is that if we multiply across? These are exact. These numbers are exact. So we really only look here for our significant figures. Multiplication division rule. 2 times 55, 85, 111.7. That's 4 significant figures. That's what my calculator gave me. 3 times 16, 48. 48.0. Now you add them up. This is addition subtraction rule. It's going to be 1 after the decimal. 8, 9, 4, 5. And that's grams per mole. Just like it was on the periodic table. Now, if I said I have X number of moles of this, how many grams? Or if I said X number of grams, how many moles? Now I have this, 159.7 grams of, and now the label is Fe2O3. Fe2O3. See what I mean? Now that's the label for 1 mole of Fe2O3. So now if you had this compound, you could do the same thing we just spent all this time doing with atoms. If you're given you could go up to a scale, you could go into the stockroom and find this label, pull it out, put it on the scale. If you put enough on the scale to have 159.7 grams on the scale, you have 1 mole of this. See what I'm saying? Okay, good. Let's do NaCl. This one's a little more simple. Na, there's 1 of those. Cl, there's 1 of those. I have some of these memorized, some of them have just never stuck. 22.99, 35.45. Yes, I remember that one. But of course, this is just 1 times 22.99, and this is just 1 times 35. You just add them up. 14, 14, 8 grams per mole. And now you have that relationship for NaCl. You guys with me?
Yes.
I'll do, well, that was 1 and 1 again. Do something a little more creative. We've been dealing with ionic compounds, but this works the same way for the molecular compounds. I said before, it's ions that come together and stick together to make the ionic compounds, and that's all we've studied so far. We'll get to the covalent compounds, but a covalent compound might be like a so look at that formula. It's 6 carbons, 12 hydrogens, and 1 oxygen. So it's the same way I did this. You're just going to go carbon, there's 6 of them. Hydrogen, there's 12 of them. Oxygen, there's 1 of them. Then you look on the periodic table. These I know, 12.01. Hydrogen is 1.01. Oxygen is 16. Calculate them across, add them up. That's how many grams per mole that weighs. So it works just the same, exactly the same for molecular compounds, which we'll study a little further out. You guys okay with that? All right. Over break, I'll get these made for you. If you're idle over break, check back on D2L and see if it's there, because it'll help you to stay caught up, but I'm a little behind. I've been up late the last few days because my dad's in the hospital. He had back surgery and it was successful, but the last few days have been harrowing for me and my family. So a little bit behind. Everything's pretty good. So you deal with that when your parents are 80 years old. That's the way it is.
Thank you.
But y'all enjoy your break.
Thank you.